Okay, we're looking at chapter 1 in Lois Roman's Computed Tomography or for Technologists, a comprehensive text. And here's the learning objectives that we're considering today. I want to give a little bit more context. We've talked some about context, and y'all may recall I showed that weird video where Gifford Hounsfield was going around collecting cow brains while listening to the Beatles. Remember that? And there was that German guy, and then we were like, suddenly we were in St. Louis, and then we were drinking beer with Rankin. I don't remember what else was going on. That's my recollection of the video, but I wanted to give us a little bit more context and pull out what's important about that history and why it's important, because it brings us up to where we're at, and it also talks a little bit about where we might go next. So that's the important thing about historical context. I'm not necessarily super interested in, do you know all these people's names or what have you, but do you have an idea of what's required in terms of the technology for the future? We'll talk about we'll give a definition of CT. So we're now far enough into the class to really define what CT is. We'll talk about how it evolved in a competitive commercial environment. And so there's a lot of different proprietary terminology. What does that mean? Different people came up with different names for the same stupid widget, right? Because you've got different people making these machines. So one manufacturer might have called that widget this thing, and someone else called it something else, because they're all trying to put their names on it. But it makes for some confusion when we're trying to learn this stuff, which is why in terms of the registry and in terms of being as broad as possible in our discussion, we'll use, for the most part, generalizable terms. So we'll talk about why that's significant. We'll relate linear attenuation, which we brushed on last week, to the use of Hounsfield units in CT, which is a powerful and significant part of CT's diagnostic capability, is tied to its ability to detect different small variations in attenuation profiles. So there's information, significant information embedded in these images that has to do with how much attenuation of the X-ray beam occurred. So then we'll move on to image acquisition, just kind of a brief overview of it, and then talking about different imaging planes, because I wouldn't want us to be confused talking about different imaging planes. So the textbook starts off doing a little bit of a bragging about why CT is better than conventional radiography. And that's great. One of the things that it does, different from conventional radiography, is it gets rid of superimposed structures. So in conventional radiography, when I'm taking a chest X-ray image of the chest, right, I see ribs superimposing the heart. The ribs are also superimposing portions of the lung. Everything's kind of overlapping. I'm seeing this one image. It's two-dimensional image, but there's a volume of anatomy there represented in 2 dimensions. So stuff overlaps. That's what superimposition means. In CT, we're able to get rid of that, right? And so this was one of the big advantages of CT from the very beginning, because the question we were asking, right, at the dawn of time is like, what magic happens when we bang rocks together, right? Our caveman ancestors took rocks, banged them together, and fire sprung out of the rocks, right? That was amazing. Pretty much the history of human civilization from that point on was just what happens when we bang different rocks together. Like, what happens if we bang rocks into the rock of the earth? Whoa, plants come out of it. What happens when we bang 2 human heads together? Oh, we can take over those people's rocks and use their rocks to bang other rocks, right? It was just this whole big rock banging operation. That is civilization. What happens if you take rocks and pile them on top of other rocks? Oh, you can live inside of those rocks. You can make like a giant cave rock that you can live inside of, right? Up until the point when, how Rankin was asking, what happens if you take little tiny rocks called electrons and bang them against a really, really heavy rock called an anode? Oh, X-rays come out of it. So it's this really big rock banging operation. Then we started to ask some weird questions. Now, what happens if you start spinning around while you're banging the rocks together, right? That is the fundamental question of CT. If you have an X-ray tube What happens if you get really wild and crazy one night and start spinning it around your head like this, right? That's the question, right? So we got a little bit up on our game. So the first thing we're able to do when we spin this X-ray tube around is get rid of superimposed structures. By spinning it around, we're going to be able to see around the corner of all these different superimposed things. So the next thing we're going to be able to do is see small differentiations in attenuation. That's what I was alluding to with the Hounsfield unit. We're going to be able to see, okay, that soft tissue structure is muscle and that is a tumor, right? And then we are going to be able to generate a superior image quality. So we will be looking at those things, but that's why she starts off kind of bragging about CT. Well, this whole operation, the textbook doesn't get into this, but I want to give us this by way of context. The first part of this question is a mathematical question. Now, I'm not going to get into all the math, right, that's required to understand this, right? But to take an X-ray tube and sling it around your head and then get a picture out of it requires some mathematics. Because if you just take the X-ray tube and start spinning it around, what you're going to get is a really blurry X-ray picture, right? You're just going to get it's going to look like something like a tornado, right? That's what you're going to get, a picture of a tornado. We don't want pictures of a tornado. We want a picture of the inside of people's bodies. So what we have to do is mathematically decompose that tornado into an anatomic image, something recognizable to the human eye. So these are the folks who did that math, Johann Radon, and they all kind of built on each other, right? Alan MacLeod McCormick, and so he was one of the people who shared the Nobel Prize with Hounsfield, the mathematician who made the discovery of how this decomposition, this mathematic decomposition works. And then Nirvana McFadden and Michael Serswat, they aren't in any way related to any of the math. I just put them on here because I like Nirvana. The thing that is important, though, is to understand that none of this would have happened without the Beatles, right? I'm not crazy on this one. So before Nirvana, there was this band called the Beatles that was arguably one of the biggest bands at the time, right? They sold a ton of records. And they sold so many records that they produced a ton of money for their record label, EMI. EMI then took that money and sunk it into research and development. So they produced that video that we watched a few weeks back about the origin of CT. EMI produced that video, right? Why? Because they're advertising this new product that they have, the CT scanner. Hounsfield got the money from the Beatles record sales, used it to work with McCormick's math, and then produced the first prototype of a CT scanner and released it for commercial use. So where are we talking about? Around 1967, right? So X-rays are discovered, 1895, right? And then 1967 we have Hounsfield starting to work on the mathematics and the prototype for CT. One of the things that's interesting is if you've ever listened to this on vinyl, Sgt. Pepper's Lonely Hearts Club Band, the last track, Eleanor Rigby, repeats endlessly. It repeats endlessly. It's an endless repeating track. It's a never-ending track. And I think that's interesting in that one of the things that we're doing now is kind of prescient. It was indicating that now we're using a iterative reconstruction reformat. We're using a mathematic process that just repeats infinitely until it has a perfect picture. We borrowed it in part from nuclear medicine. So around 1971, we have the first prototype CT scanner transitioning into actual medical use. Hounsfield got this idea. This is him smiling and looking at a cow brain here. While he was walking around Sherwood Forest, like Robin Hood country. He was walking around, he grew up in Nottinghamshire, was walking around the forest one day and had that great idea. What happens if you swing rocks around your head while you're banging them together, right? and CT was born. So that's an illustration of the first prototype CT scanner. And you can see right here, this right here is literally just a record turntable. It's a lathe. So I say all that to say, the reason I'm interested in that, I don't necessarily need you to know those names. Knowing 1971 is helpful, right? That is helpful to know that early 1970s is when CT broke out into medical use, right? But I want you to know that everything moving forward now, as we look at where will CT be 5 years from now, 10 years from now, it is going to look a lot like what just happened. There will continue to be records that are sold by bands that make people money, and that money will generate additional research and development into fields that are very different from music, fields like mathematics, right? Fields like computer design and graphics. And we'll continue to see these developments out from culture to mathematics to technology. Culture to mathematics to technology. That's what I anticipate will happen. And so the things that you like, the artists that you like to listen to now, you may not think about this, but they're having an influence on that building process, right? And it's exciting to see that. It's exciting to be a part of that. Well, what is CT? What is the best way to design that, to explain it to our patients? This is looking at our textbook. She says, think about a loaf of bread. And you've probably heard people make this comparison before. It's a really useful comparison, right? What we're going to get is images that are cross-sectional through that loaf of bread. So like slices through the loaf of bread. To where if the crust represents something on the patient body, it's the skin. And the stuff inside the bread, like let's pretend it's raisin bread. The raisins and the cinnamon and the wheat flour and all that inside the bread are different organs and parts of the patient's anatomy. So we're able to see slice by slice the entire loaf of bread. We're able to see it in different orientations. So because this is built off of mathematical processes, we can look at the raisin from different directions. We can see it axially, right? So we can look at the raisin in an axial slice, like a bread slice. We can also basically recombine it mathematically and now slice the bread lengthwise and see that raisin from a different direction. We can slice this loaf of bread and unslice it over and over and over again. We can slice it and then we can put the loaf of bread back together. And we can slice it in a funny angle, like an oblique angle, an angle that no one would ever slice bread, right? So we can slice it any which way that we want it. So as you have that kind of bread loaf in your mind, think about that. That essentially what CT is, it literally means, tomography means cutting image. It means slice image. So we're using a computer and the mathematics of the computer to create slice images. That's what CT means, to me. So the idea of cross-sectional images is directly tied to CT. So we all had to take cross-sectional anatomy. That class is basically CT 101, right? Everything that you learned in cross-sectional anatomy, we will be using, even in this class, even in the course of this class today, as you're picturing this stuff, be picturing those cross-sectional anatomy pictures that you were looking at. More than that even, be able to take the patient's body apart and put it back together in different slice directions. Because really what we're interested in is not just the slice pictures, we're interested in how those pictures tell a story. They tell a story about a three-dimensional volume in space, the patient's body. So it's not just enough just to look slice by slice and say, oh, that's the pancreas, that's the spine. We need to be able to think about how all of that interconnects three-dimensionally. Because this slice-wise way of thinking is three-dimensional. So that's the major transition to go from X-ray, right, two-dimensional, everything superimposed, to CT three-dimensional. We're adding all this stuff together. So each cross-sectional slice represents a specific plane in the patient, right? And the thickness of that cross-sectional slice is referred to as the z-axis. The z-axis. So we have a patient laying on our CT exam table. Let's pretend that this is my CT exam table, and someone is laying on it, right? Their head is that direction. And that's where the gantry is at. The CT machine is that way. I'm going to raise this table up, and I'm going to fly it through the big donut hole, right? As they're flying through that donut hole, basically the direction of travel through the donut hole is the z-axis, right? It's the z-axis is their direction of travel. As this table lifts up and flies through that donut hole, the z-axis is the direction of that table's travel. That will always be the case. It's generalizable. Every CT scanner you ever work on, that will be how it works. Of course, I think radiation therapy made it confusing. Bell's table is a little bit different.
I think ours is the same.
The z-axis is the same. What I'm not certain about similarities-wise is the x and y-axis. So as I'm flying this patient through the gantry and taking slice-wise pictures, right, each little slice that I'm looking at is just x and y, right? X and y. I go to the next slice along the z-axis, there's x and y again. I go to the next slice along the z-axis, and there's x and y again. So the thickness of each one of those slices we'll talk about as the z-axis. So I will very seldom say z-axis. It's hard to say, it's weird. What I'll talk about is slices. And every time I'm saying slices, please just you be thinking, he's saying something really smart and mathematical about the z-axis, right? Assume that I'm smarter than I look or something. So here is an illustration from the textbook of how the data is built, right? So what we've got are these little tiny pixels. Because as we go through each slice of the patient's body, as they fly through the donut hole, right, what this machine is doing is, number one, it's spinning a X-ray tube around the patient's body with an image receptor, and it's taking the information that it's getting from the image receptor, and it's putting it on a matrix, right? Now, a matrix is just a fancy word for something that has X and Y values, right? I think about it as being like a chest of drawers, a big chest of drawers. So each one of these squares in this matrix is a drawer, and I can put things in that drawer. The computer's storing different things in that drawer, right? The stuff that it's storing in that drawer is information about each piece of the slice of bread. It's carving the slice of bread into little tiny dots, and it's sticking those little dots into different drawers, right? The reason it does that is because that's the way computers think. So that's just how computers work. They need to store data somewhere. And so a matrix gives us a spatial way of storing data, to say that this is the way the data looks in space, inside the patient's body. I don't mean outer space, I mean in the volume of the patient's body. So it takes that information and drops it into different drawers. The width is the x-axis and the height is the y. So if you're looking at the picture, right, and you're scanning from left to right on the CT image, just one slice on a CT image, that x-axis is basically, again, left to right on the patient's body, if they're laying on their back on this CT table, and the y-axis would be up and down, just like with a normal Cartesian graph, like what we did in trigonometry and geometry. It's the same x and y-axis, x and y-axis. Okay? But now we're saying those are locations in the patient's body. So, critical thought, right? If I've got a little patient laying on this exam table, right? Their head is that way. They're supine on this table. What would the top of the y-axis represent on the patient's body? Would it be anterior, posterior? It would be anterior. Good. And as I move down the y-axis, I'd be moving more posteriorly on the patient. Right? As I'm moving right to left along the x-axis, I'm doing just the same with the patient, only this is the way a doctor once explained it to me. Imagine you're looking up the patient's skirt, right? I don't know, it's stuck in my mind. You're seeing the pictures flipped. So for us as as X-ray techs, we're comfortable with that. What I'm saying is the patient's right side is on the left side of the picture. So if you imagine you're looking at me and we're staring at each other, your right hand matches my left hand, right? And your left hand matches my right hand. That's what we're seeing on these pictures. That's what the doctor meant when he said, imagine you're looking at the patient's skirt. So you wouldn't get flip-flopped. Because I'm constantly having to remember, okay, yeah, that's the liver, but it's on the other side of the picture from what I would expect, right? You're constantly reminding yourself, oh, that's the patient's right side, that's the patient's left side. We're normally pretty good with the y-axis. Moving up and down on the y-axis, ant to post, that's pretty obvious. With the left to right thing, I see students get tripped up. So, I've already kind of alluded to this a little bit in the conversation, the brief conversation about how radiation therapy may have labeled axes differently, right? That goes back to all these different manufacturers that are out there. Like think about how many different types of vacuum cleaner you can buy, right? There's a ton of different vacuum cleaners out there, and all of them are a piece of crap, right? And they all got special suction things. Like one person calls it like the shark tube, right, or something. The next person calls it like the carpet destroyer, and the next one calls it like the dust smiter. Like they've all got these different stupid attachments on them. A CT scanner is the same way. These people, as they started to develop the things, they all wanted to carve up their little piece of the pie, right? And so as an example of different proprietary names for just a scout, just an initial lining up picture, you've got Siemens calling it a topogram, GE calling it a scout, Toshiba calling it a scanogram, Picker calling it a pilot, and then I'm just calling it annoying, right? It's ridiculous. For the most part, I just go with whatever is shortest. So of that list, scout. It's short, GE. For other people, I'll jump around. I might use a Siemens term for something, and I apologize for that. Primarily, my training has been in GE, Siemens, and a little bit on Toshiba. But Toshiba I seldom use because pretty much everything Toshiba calls is annoying and like way too long, right? So know that. If you're confused, if I start talking about, oh, the scout did this or the scout did that, and you have no clue what I'm saying about this wonky term, please raise your hand, because chances are no one else knows what I'm talking about, because I'm talking about some weird specific thing about Siemens, when really I should be generalizing, right? It's a trap that I fall into. The textbook points this out on page 4. So we need to be able to generalize this. Unfortunately, to do that, oftentimes, yes?
So are we going to be tested over the different words or is there just a general word for each one that you're going to tell us, focus on this one, not this?
Good, that's a great question. Yes, I will give you the specific term. Right, I'm not curious, like, what does Siemens call a lineup scan, right? I'll just call it a scout.
Gotcha.
Great question. Other questions?
So in most clinical settings, when you, like where I'm at now, there's a GE, and I know they use the term scouts.
Yeah.
But like, let's say the next clinic that I go to, they have a different type of CT, will they still sometimes use the word scout?
They probably will.
Or
yeah.
Is it something that's embedded in their programming that shows that word, so you have to go with
it? It is embedded in the programming. It's embedded, like when you're working on the GE scanner, it says initiate scout, right? Versus if you're on a Siemens, it says scanogram or something ridiculous like that. So yes, it is embedded in the programming, but pretty quickly technologists would pick up, oh, that's one of the reasons why when I'm introducing myself as a CT tech, I say right off the bat, I'm trained in GE and Siemens. Because then the other techs know, oh, this is the language he talks. He talks GE language, right? Or he knows Siemens language too, that's helpful, right? So yes, it is a little bit of a translation, but you can get over that pretty quick. Great questions, awesome questions. So, all of these structures that we're going to see inside the patient's body, inside of our little bread loaf, are going to be represented as different shades of gray. Basically, the creation of these shades of gray is based on attenuation inside of the patient's body. Right? So we talked a little bit about this last week, but let's further define what's happening. So the degree to which the X-ray beam is reduced by an object we will call attenuation. And that's an umbrella term. It relates to anything that reduced the intensity of the beam exiting the patient's body toward the image receptor. Right? So we've got an X-ray tube on one side, we have an image receptor on the other side, and we're spinning them both around the patient, right? As the X-rays strike the patient, they are attenuated. Some of that attenuation is photoelectric absorption. Some of that attenuation is Compton scatter away from the image receptor, right? And then we have that beam exits the patient and strikes the image receptor, right? Whatever that image receptor catches of that remnant beam, right, we are going to use to make a picture, right? So another way to think about this, the simplest way to think about this is, what did you have to start with and what did you have at the end? Between the two of those is a picture. What you had in X-rays to start with and what you had in X-rays at the end. Between those two is a picture. It's a ratio. It's a statistic, in other words.
Can you say absorption?
Absorption is another way to talk about this, yes. The physics nerds will probably be trolling this video at this point, but yes, I'm fine with you saying absorption. The nice thing about attenuation is it specifically almost always applies to radiation interactions of electromagnetic radiation, right? Whereas with absorption, there's other properties that can be absorbed, right? We could have like heat absorption, something like that. Okay, so the photons pass through the objects unimpeded. If the patient's body does not stop the X-rays, it shows up blacker or more dark on the image receptor, right? It's going to hit the image receptor more. When the X-rays are completely absorbed, when the photons are completely absorbed by the object, those show up white on the picture. And then everything between those two extremes of color, black and white, various shades of gray, is everything in between complete absorption and complete transit. So, whether or not those X-rays bump into things and keep going or bump into things and stop has to do with what's going on inside of the patient's body. So the number of X-ray photons that interact depends on the patient's body, its thickness, the actual physical thickness of the patient's body, how broad their shoulders are, how big their belly is, how big their head is, right? All of those things we will refer to as thickness of the anatomy, the physical density of the anatomy. So, I was asking this question of the X-ray students last week. If you had a choice between getting hit in the head with a block of ice or a bucket of water, which would you choose, right? Hopefully we would all choose the bucket of water, right? Why? They're exactly the same molecule, right? In terms of molecule, water is water is water. It's H2O, right? They are in different states of, what's the term that slipped my mind? Different physical states, right? One's a solid, one's a liquid. That's what I mean by density. The ice is more dense, right? The ice is more dense. It would hurt more. So the ice would show up wider on the picture than the water because of its density. And then atomic number. Finally, atomic number. So if there's metal in the patient's body, it's going to show up what color? White, right? If there's air in the patient's body, it will show up what color? Black, right? So we have a little review question. This is not showing up on my YouTube video, but it shows up here. Air in the lungs is considered what?
Low attenuation.
Good, low attenuation, awesome. So because it's that low attenuation, it's going to be showing up wider on the image. Excellent work. Y'all are so smart. So that's great. And in the world of X-ray, that's kind of it, right? But in the world of CT, that's just half of it. In the world of CT, yes, question?
On the last slide, did that say that the lungs show up in white? Or did you, because you just confused me when you said that.
I said that wrong. I said it wrong. Thank you for catching that. So the lungs are going to show up black because they are low attenuation.
So the bone would be high to absolute attenuation, whereas nothing being there is low to no attenuation.
Correct.
Okay.
Yeah, I'm so glad you caught that.
Thank
Yes.
you.
So the lungs are low attenuation. They will show up black on the image. The bones are high attenuation. They attenuate a lot of stuff, so they will show up white on the image. Well, so like I said, this is really only half of the story so far. We need to figure out a way to quantify that. That is the computer part of the tomography, right? That's the computer part. The computer sees a lot more data in a CT image than you or I do. We have to work with the computer to see all the information that's in the image. So that's a big part of this class, is figuring out how do we work with this computer to see everything that's there. So pay attention for this next part, because we're going to be talking about the other information that's there. So we've referred to how to orient ourselves in terms of cross-sectional anatomy inside of the image. You know, whether we're ant to post, or patient's right or patient's left. That's one half of the story. The other half of the story is talking about this attenuation piece, right? And this is the part that students trip on the most. That's why I'm spending so much time with it. It's tied to a unit called the Hounsfield unit, named after Gifford Hounsfield. This is an expression, a simplified expression of attenuation profiles. The Hounsfield unit is a simplified expression of attenuation profiles. So for there to be a perceived difference in attenuation on the in the image, that attenuation difference has to exist in the patient's body, right? Then we can see two different organs, right? The computer can see the difference even if the human eye can't. And so it ties that difference in attenuation to the Hounsfield unit. So it's a way of quantifying beam attenuation. Sometimes it's also called CT numbers or density values, or you'll see it abbreviated HU, right? That just stands for Hounsfield unit, right? In nuclear medicine, we have what is the standard uptake value. Similar kind of idea, right? A way to quantify what's happening inside the patient's body. And that what's happening inside the patient's body is a big question. Like if we look on page 7 in the textbook, we see an excellent illustration of where the Hounsfield units would help us out. So we have the patient's body without contrast and the patient's body with contrast. We can see that the kidneys appear brighter on the image. Their Hounsfield unit would be higher. They are attenuating more, and that's why they're showing up wider on the image. It's because we've administered IV contrast. So when we inject a patient with IV contrast, there's going to be more attenuation happening inside of organs that have a lot of blood inside of them, right? And so we would expect to see the Hounsfield units go up, right? So this is the scale. 0 is water. Water is 0 on the Hounsfield scale, right? And the textbook says he arbitrarily chose that. I don't think it was arbitrary. I think he was very smart, and he knew that the body is like 85% water. If we're going to zero it out, let's zero it on water. Anything that attenuates less than water will be negative on the Hounsfield scale. So one of the weird ones, fat, is negative on the Hounsfield scale. Well, how is that the case? Well, if fat floats on water, right? So it attenuates less than water. It's negative on the Hounsfield scale. Air is very negative on the Hounsfield scale, like negative 1,000 would be room air. Well, what's positive on the Hounsfield scale? Anything heavier than water, right? So gray matter. Gray matter has a mixture of proteins and fat, and so it's going to be one of the first things that we'll encounter as we're going up the Hounsfield scale. Then blood, right, is heavier than water because it has blood cells in it. There's a lot of water in blood, but there's also all these little tiny cells in blood. And then things like bone and muscle and stuff like that, different organs, will be positive on the Hounsfield scale. Of course, IV contrast would also be positive on the Hounsfield scale. All this information is embedded in the image. And at any point on the image, you can drop a little measuring device called an ROI, a region of interest. You can draw a region of interest on the image, and you can measure the Hounsfield units there. So if I'm curious, what's the difference in the Hounsfield units between the kidneys here with contrast and the kidneys here without contrast? I just draw a little circle around the kidney, and it tells me the Hounsfield unit difference for the kidney. All right? That's a region of interest. We'll be talking about it. It's not in the slide presentation, but we'll come back to it, I promise. So again, 0 is going to be water. Negative 1,000 is air. A positive 1,000 is going to be dense material such as bone. And I'm sorry for the way the bullet's formatted on this. That looks like it's saying like a negative sign. It's not a negative sign. That's just the bullet, right? Values higher than 2,000 represent very dense materials such as metallic stuff. So total, when we look at the whole Hounsfield scale, we've got everything from negative 1,000 to positive 1,000. There's 2,000 possible Hounsfield values, right? So if I'm moving more negative on the scale, I'm going down in attenuation value. If I'm going more positive on the scale, I'm going up in attenuation value. Total, there's 2,000, yes?
So, like, naturally, the highest you can go is 1,000, but if there's, like, metal in the body or there's contrast, it could be higher.
Yeah, and what that means by naturally is like stuff that is part of the human body. So the Hounsfield scale is honed in on what is normal human anatomy. We're going to represent everything in the normal human anatomy as a number from negative 1,000 to positive 1,000 for 2,000 possible values inside the human body. Great question. Now I want to be real clear about the way I'm using the word volume. I am not talking about it like what the volume of music is or something like that, or the volume of my step-parents' cell phones in public. But this volume has to do with a set of space. We can think about it as like the way that we talk about volumes in physics class. So generally the way that I'm using volume is in reference to the patient's body. I'll talk about what is the volume that we're interested in scanning. I'm saying what area on the patient's body are we committing to make slices of, right? What is the area of interest? So we even have things like a VOI, a volume of interest, right, that we're going to define. So this process that CT uses to differentiate different attenuation values is averaged to produce a pixel, right? So as the X-ray beam passes through the patient, it's either attenuated or not attenuated. It either strikes or doesn't strike part of the image receptor, and that information is averaged and put in a drawer, right? The next little drawer along, the beam passes through the patient, it's attenuated or not attenuated, that's averaged and put into a drawer, right, in our matrix. This process is going to be affected by slice thickness. What do I mean? So to go back to our bread analogy, let's say we've got raisins in a loaf of bread, right? And we're making big, thick slices, like 2-inch slices through the loaf of bread. Is it possible I would skip a raisin? Yes, it's very possible I would skip a raisin. The same thing can happen in CT. I can be making big slices through the patient's body, and is it possible I would miss a kidney stone? Yes, it's possible I would miss a kidney stone, right? Because the information, again, is being averaged and put into a drawer. So I could average out the kidney stone, right? Yes?
Is there, just a general thickness that's used, or does it vary depending on what you're scanning for?
Awesome question. Yes, it will vary depending on what we are looking for. So CT techs are like nerd level interested in why are we doing this procedure, right? What are we looking for? Because if you just say CT abdomen, that tells me nothing. Is it a CT abdomen for kidney stones? Is it a CT abdomen for kidneys, for kidney cancer? Is it a CT abdomen for pancreatitis? Those are 3 different exams, right? So CT abdomen really tells me nothing. It tells me the volume, but it didn't tell me how that volume should be averaged. What should be the slice thickness through that volume, right? If it's kidney stones, I want a little tiny slice thickness. I want little tiny slices so I can see this little tiny thing, right? If it's cancer, I want the slices to be a little bit thicker, but I want contrast to be there so I can see the difference between the tumor and the normal tissue. Because the tumor loves blood, right? So it's going to drink up that IV contrast, right? If it's pancreatitis, I need to have some images without, some images with, some in an arterial phase. I need a bunch of different contrast phases. Yes, another question.
So when you say averaged, are you saying like you're taking the slices and what those numbers are, they get added together to give you an average number for the whole?
Good. Yeah, let me hit pause on this real quick. Okay. So this is one helpful thing to understand. Like I mentioned before, if we just take an X-ray tube and swing it around the patient's body, we're going to get something that looks blurry, like a tornado, right? We will call that raw data. The generalized term for that tornado of information is raw data. It is literally what the image receptor saw, was just this blurring, swirling streak of information, different attenuation values flying at it as it's spinning around the patient's body at speeds approaching 100 revolutions per minute, right? I can't look at that and see jack, right? I can't look at a tornado and guide any kind of patient care. So we had to figure out a way to take that tornado of information, that raw data, and create an image out of it, right? That's where the math was important. Because in essence, what we're going to do is similar maybe to like the end of the Wizard of Oz or something. We're going to spin the tornado backwards and put the house back down, right? So the tornado went through the house, it blew the house to pieces, and now I can't see, is that the front door? Is that Dorothy's dog? Is that the next door neighbor? I can't tell what's going on right now, right? Let's spin the tornado backwards, put it all back together, right? The fancy term for that is called filtered back projection. We're filtering out the noise, and we're just spinning the tornado backwards. Filtered back projection. It's not in this chapter, we'll be talking about it. That's the way that we get from this raw data to the image data. So we take that tornado, we spin it backwards, and now we've got a picture that I can look at and I can say, that's a kidney, and it has a kidney stone in it. Or the doctor can say, That's a cyst, and we need to pop that thing, right? We need to get the impurities out of it or whatever. So raw data is all that data that's collected. Sometimes it's also called scan data, just for added confusion, right? I think that Siemens calls it a histogram or a scanogram. It's raw data. Siemens is cool in that it actually has an image of what the raw data looks like, which is just kind of interesting to look at. I have no clue what I'm seeing, but it really does look like a tornado. The image data is going to be what we would actually use. We're going to take that raw data and average it all together, tie it to a pixel value, each pixel value to a Hounsfield unit, and orient it in space so that we can see slice by slice through the patient's body. There's two different ways, yes?
Sorry. So the volume average,
Mm-hmm.
does that come from the raw data, or is that the image data?
That's a good
Because
question.
The numeric value that it gets assigned,
There's going to be a lot more averaging on the image data than on the raw data.
okay,
The raw data is really just kind of, this is what happened at the image receptor.
so then you could probably assume that the averaging, the numeric averaging that takes place is probably with the imaging data.
Correct.
Okay.
Where we start to worry a little bit is if we don't have it, if it's not in the raw data, we cannot represent it, right? So if the slice was too thick and we did not see the raisin in the raw data, no amount of messing with that raw data is going to produce the raisin. We needed to have a better protocol to start with, right? But yeah, short answer, yes, it's primarily with the image data. So there's two different modes that we scan in. For the most part, almost all protocols now have moved towards helical, right? So, but there's two. The first we'll talk about is axial. That means step and shoot. So you advance the table through the gantry, you spin the tube around them, get a picture, move the table into the gantry, spin it around the patient again, get another picture, move the table into the gantry, spin it around the patient, get another picture. We're moving the table, spinning the gantry, and taking the pictures in that sequential order. Step and shoot. Table moves in, scan, table moves in, scan, table moves in, scan. Yes?
In radiation therapy, like the external beam, I've seen them say the same thing, step and shoot, in some of the treatment plans.
Certainly.
Is that the same thing?
It probably is. I'm not super familiar with like the cone beam CT stuff that's done. But yeah, I would assume that the gantry, a radiation therapy gantry would have a very difficult time doing helical scan modes. It would have to do an axial scan mode, just because of how big that machine is. Make sense?
I didn't know if they were, I didn't know if in external beam it meant, the gantry moves, delivers dose, moves, delivers dose, moves, delivers dose. If it was the same principle like with CT where it scans, then it moves.
It's not.
Scans, then it moves.
That's a different process.
Okay.
Yeah. So this axial thing is going to give us slice by slice through the loaf of bread. With the early technology that we had, like when we were literally putting cow brains on record turntables, that's all we had the computing processing power to handle. Like the very first CT scanner, it required almost a day to process images. It had very little processing power, right? So it was a limitation of the technology, it was a limitation of the computers that we had. We had to rely on axial scan modes. So for particularly imaging that required high resolution images, like for example a brain scan, we used axial imaging for that. We were not going to have as much volume averaging happening with an axial scan mode, right? For the most part, our computers have gotten better and our technology has gotten better. So for most scanners that are being produced now, the axial scan mode is not necessary. We get fine spatial resolution. We get beautiful pictures using the helical mode. So what is helical? Helical is more like a honey-baked ham. It is a spiral slice where the table is moving at the same time that the scanner is scanning. There's none of this step and shoot stuff. It's just moving the patient through the scanner, and it's getting this big spiral slice. Why is that helpful? Well, the short answer is that this is now volumetric data. It represents the entire volume as a single thing in the computer's mind, or the computer's memory, I should say. The volume of data is a single continuous thing. And so if I need to, now I can represent that entire volume of data three-dimensionally. I can show the entire heart as a three-dimensional object. I can 3D print it. I can send it to radiation therapy for dosimetry because I have a three-dimensional volume of data. That is the power of helical scanning. So I will use the term helical and volumetric interchangeably because basically volumetric is the power of helical, and it is the way that you start to think about things. Regardless, though, it's still helpful to have some waypoint and directional terms. So we will use the exact same directional terms that we've used in sectional anatomy, et cetera, et cetera. I'll be constantly reminding you to refer back to how the patient's body is, right, on the image. But I'll use terms like anterior, ventral, posterior, inferior, superior, distal, proximal, those types of things, right? There's fancy terminology that you can use in the head, like rostral versus caudal. I probably will not use those terms, right? But these are the terms that we'll use for the most part. So, how those are represented on the image are in these different planes, right? And so any one of these planes represented on this, plus an oblique front plane, can be represented as a CT image. So if I have helical data, if I have volumetric data, I can produce images in any one of these planes. Most of the images that we will be looking at will be in the axial plane. But we can produce them in the sagittal, coronal, oblique planes, any of these planes. We can also, like I've already alluded to, represent them as three-dimensional. We could take this entire brain and rotate the entire thing around. That's what I mean by three-dimensional. So just to review our knowledge about imaging planes, an image plane that divides the body into right and left sections is called what? Good. That is going to be in the sagittal plane. And so in the same way now, as I'm looking at an image in the sagittal plane and I advance to the next image, I'm advancing to the patient's right or the patient's left. So as I scroll through those pictures in the sagittal plane, I'm moving right to left and left to right in the patient's body. So bear with me, kind of stay in that three-dimensional frame. If we're looking at a coronal image of the patient's body, and I'm scanning back and forth, I'm scrolling back and forth through those pictures, how am I moving through the patient's body? Perfect. Awesome. So the final piece to this puzzle is kind of how to break down this process into discrete steps, into the steps that the CT scanner goes through to produce a picture. The first, in general terms, is data acquisition. I have the couch raised, and I'm moving the patient through the tube while I'm spinning an X-ray tube around their body. That is data acquisition, right? Then image reconstruction. Now that I have that raw data, image reconstruction is the process of spinning the tornado backwards and making a house, right? So I'm going to basically spin the patient back out of the tube and make a picture, right? And then finally, image display, looking at it, right? Now that may seem like a completely obvious one, but I promise you there's a lot to be done with these pictures that's not immediately apparent, right? There's information embedded in these pictures that goes beyond what's readily there all the time. So there's different ways of looking at it. And this last thing I'll say by way of thanks is just, I like this. It's actually tying the Hounsfield scale to different gray and white values. And it's helpful again to remember, as we go up on this Hounsfield scale, we'll expect the colors to get whiter. As we go down on the Hounsfield scale, we'd expect them to get darker. Thank y'all so much.